Hi, we are moving along and we're on chapter 1.3 in Chem 109, How Matter Changes. Okay, we've talked about matter. Remember what matter is. It's something that has volume and it takes up space, right? So a physical change, whenever we're thinking about matter, that's a change in the state of matter. Okay, so that's a change in the form of matter. So we remember the three forms of matter, right? So we have solid, liquid, and gas. And so this is the physical change. The identity remains the same. And you can see what your textbook and the slide is trying to illustrate to you is that the chemical does not change here. For example, if you have an ice cube, right, regular ice cube, H2O, water, we have the solid form of water, and if we heat that a little, that ice melts and becomes liquid water, still H2O, right? There's no chemical change. And then if that becomes steam, that's still H2O, right? So that's what I mean by a change in the form. That is the physical change. And that is in contrast to the chemical change, right? So in a chemical change, it's just like the term suggests. It's a change in the identity of the substance. So in the physical change, the identity is not different. Water is water, no matter whether it's a solid, a liquid, or a gas, right? So in this example, you see this picture of this coal here. So if you have some carbon, you have this coal, you're going to barbecue and it burns with oxygen, you're going to produce carbon dioxide, right? That's a chemical reaction, right? You started with carbon and oxygen and now you have carbon dioxide. Okay, that's a chemical change. It's different, right? And that's a chemical reaction. And so you're going to see in the next slides how we actually write this out as scientists. This is just sort of a very primitive way of writing it out. But in the next few slides, you're really going to understand what I mean. The way we write chemical equations is very important. It's illustrating to other scientists and backing our own knowledge of exactly what we're doing. And it helps you to understand like what's happening, what is being created or produced rather, not created, because matter what cannot be created or destroyed. And you're going to see that in the next slide. You're seeing what can be produced with what. Okay, we talked about the coal burning, right? This is that reaction written out with the chemical symbols and the chemical formulas that we've mentioned before, with the chemical symbols for our elements here, carbon and oxygen. And you see that we've got a compound in this, a chemical formula for a compound in this chemical equation. It shows what happens to the substances involved in the chemical reaction, okay? This is how we know what we need to produce what. Carbon and oxygen in this particular example are the reactants, right? you have that coal, you got the carbon, you've got oxygen there, right? And they are reacting together, with heat, with applied heat, and they are going to produce something. Like when you react, it's a response. What is produced? And so the components involved in the reaction that react together are called the reactants. And you see that here, these are the reactants. Okay, so when they react, what did they produce? So it's just like if you react to something, that response is that's the production. It's the result. And here we have a product. And in this case, you have the arrow that means react to form. And so in this case, they are reacting with heat. Carbon is burning with oxygen, right? And so you can see clearly here is one carbon atom and two oxygen atoms, and they're reacting with heat to form carbon dioxide. This chemical formula tells us exactly what's happening, okay? We know which elements, we know how many. And also something new, you see that the forms of matter are included here. S for solid, L for liquid, G for gas, and AQ for aqueous just means dissolved in water. For example, if you have NaCl, this is like your Morton's salt, this is table salt. If you write with S, the solid form. If we want to say salt water, dissolved in water, NaCl, AQ, aqueous, right? And so what is something really important about chemical equations is the fact that you have to balance them. Because why do you have to balance them? You have to balance them because of this thing that exists called the law of conservation of mass, meaning that matter only changes form. It is not created or destroyed. It's not a beginning or an end. It just changes. Therefore, you must have the same number of atoms on one side of the equation that you have on the other. The same number of atoms in the reactants for those specific elements in the products for those elements, right? And you can see this written here. Matter only changes form, so the amount of matter on the reactant side and the product side must be equal. That's why the equation has to be balanced. There's a meaning to that. It is fun to do it, but we're not just doing it for fun. It illustrates the law of conservation of mass. We can balance the equation by adding a number called a coefficient in front of the chemical formula for a substance in the chemical equation. Okay. And so basically before, when I mentioned if you do not write subscripts, also remember to assume that means that there is only one atom. And I'm going to show you exactly what I'm talking about with coefficients. We're going to work some problems. Okay. Before we start, here's a list of, or rather a protocol sort of for you to follow, a little checklist to make sure that a chemical equation is balanced. Your chemical equation that you're looking at that's important to you is balanced. First, you have to decide, is the chemical equation balanced? Second, you have to balance the chemical equation, and you've got to be careful. And something that you should do is balance elements. Remember this when working the problems. that appear only once on a side first. If you don't do this, you're going to have to probably repeat balancing the equation. You're going to have to start over, and you'll see that. And step 3, check to see if it's balanced. So is it balanced in the first place? Most of the time with these problems, it's not going to be balanced. Then balance the equation, okay? So balance it, and that's like a terrible little illustration of a balance. And then, once again, ask yourself, is it balanced? Right? And our next section is going to be math counts. So this is just the beginning for the math that we're going to be working on in the next couple of sections. Here are our problems. We're working on the odd ones. And we've got 1.11, and you're going to do the evens. Determine whether each of the following is a physical change or a chemical reaction. A copper penny turns green. And this is not, maybe just as it seems, you may think, oh, well, that's physical. I can see that. That's not how this works. Think of what is copper, something copper that has changed green over time that you know of, right? The Statue of Liberty. It wasn't always green, right? Oxidation happened. And so that's why a copper penny would turn green. That is, in fact, what? That is a chemical reaction. That is not just a change in form. That is not a physical change that we're looking at. B, sugar is melted to make candy. Well, is it that easy to get rid of the sugar just by melting it, or creating caramel? No, sugar is still there, right? So that is a physical change, right? An antacid tablet is dropped into water and bubbles of carbon dioxide are formed. Well, you are releasing something there with bubbles of carbon dioxide form, okay? Think about that. Whenever you used to make your volcano experiments in elementary school, that in chemistry class, right? That is a chemical change. You are forming, carbon dioxide is being formed, okay? That is the product. So that is a chemical change that can be written with a chemical equation. That's a chemical change. All right. Moving on. 1.13. Balance each of the following reactions by adding coefficients in the blanks. For the purpose of this exercise, place a 1 where appropriate. Usually, if no coefficient appears, 1 is implied. Okay, you already know that. Let's say we're going to call these X and Y. These are X and Y atoms. Gray is X and orange is Y. So here we have, this means that would be X2. That's 2 atoms. So we have our subscript, and we have Y2. And here we have X, Y. So these are implied, these are 1, right? So how is this balanced, first of all? Well, we have 2X here, 1X here, right? 2X, 1X. And here we have 2Y and 1Y. All right. So what can we do? Well, let's see. X is all by itself here as 2. The other side is 1. We need to increase this. So we're going to put this coefficient in the front. And if you multiply this coefficient by this implied subscript here, you get 2. That's 2 atoms. So that's what we do with the coefficient in the subscript. We multiply. And we have 2x, so 2 times 1y. So we have 2x and 2y on the reactant side. And on the products, we have just x2. We don't need to make this any bigger. So the coefficient here is 1. And here we have 2y. And on this side, we already have 2y. So we just say just say 1. So 1 times 2 is 2. 1 times 2 is 2. 2 times 1 is 2. 2 times 1 is 2. So is everything the same? Is this balanced? Yes. All right. B. Is this balanced? Here we have x2, y2, and here we have x2, right? y1. Is this balanced? Probably not. So why is it not balanced? Let's look at it. We have 2 x's. We have 2 y's. Here we have 2 x's, so the x's check out. Oh, but my y's don't. So how are we going to fix this? So it looks like to start off with, we really would not need to change the x's. Let's look at the y's. The y's is what is in balance, and let's see on this side with the products. We have 2y. Basically, we need to increase y on the reactant side in order to balance this, right? And so if we put a 2 here, so now we have 2y, okay? And here, if we put 1, then we have 2y here. My y's check out. But what about x's? So here we have now 2 times 2, we have 4x. And here we only have 2x. So how can we solve this? Well, 4 divided by 2 is 2. So now, right, we have 4 x's and we have 2 y's. And here we have 4 x's and 2 y's. So this checks out, right? So basically, this is the chemical equation for the reaction of water. So you have okay. All right. So if I need to take that slower, anyone just let me know. It's important to really understand these foundations early on. All right. So let's work on 1.15. Add coefficients to balance the chemical equation shown. Let's sort of blow this up so that you can see it better. Right. So here we have aluminum and A plus chlorine. We have AlCl3. So let's see. Are these reactants and products balanced? Right? Well, we have 1 aluminum here, 1 aluminum here. We have 2 chlorine, and here we have 3. No, we're not balanced. So a trick that you can use, you can look, and if there is some sort of common factor that you can use, that these are both multiples of 6. Okay, so you can swap these subscripts for coefficients. Watch what I mean. Let's see if it works. So here, this chlorine on the reactant side is 3. So we're going to put 3 over here. And on the on the reactant side, rather, is 2. So let's carry this 2 over. So we moved the 3 from the products to the reactants and the 2 from the reactants to the products. And what do we have? We have, let's see, our chlorine is 6 because 3 times 2 is 6. And we have 2 times 3 is 6 for chlorine. All right, you see what I did there? Now, what you've also done, let's check aluminum. Now you have 2 times 1, you have 2 aluminum atoms, but you only have 1 on this side. So how are you going to fix that? Let's just add a 2 there. There you go. So, that should, let's see. Does it look balanced? It looks balanced to me. All right, I think that is correct. So we can move on to the next one. I'll change the color so that you can see a little better on the next one. So here on the reactant side, let's look at all of our elements and see if they're balanced. We have 1 hydrogen here, and we have 2 hydrogens here. Okay, so we already have an issue. We have chlorine, just 1 here, and chlorine we have 2 here, so that's another issue. Zinc, only 1 of each. Okay, so let's start with, there's only 1 on one side, and that's hydrogen. All right, we have 2 hydrogen, so we know on this side we're going to have to increase the number of atoms. So let's put a 2 there. Okay, so now our hydrogens are balanced, but look, we've got to realize we've increased the chlorine here, and we've got chlorine on the other side. But how many are on the other side? Oh, 2, and now there's 2. Look, it looks like I've totally solved this equation. Yeah, it looks right to me. Checks out. All right. So let's change the color again. Okay. Let's see. So here we have silicon. Let's look at all of the elements and see we've got 1 here. And we've got 1 on the product side. On the reactant side, we have oxygen 2. And here we have oxygen 1. Okay, there we have an issue. And look, here we have carbon 1, and here we have carbon once and twice. So we have 2 carbons. Okay, so we see carbon by itself on this side. So we're going to have to increase this. Okay, and I'm going to pick, let's see. We know that we need to increase carbon, and we also need to increase oxygen though. Okay, so let's see. If we increase oxygen, because we know we've got to increase carbon, we've got oxygen all right there. So let's see. That's an easy fix, right? 2 oxygens, 2 oxygens. Okay, but what did I do? Now I've made 2 carbons on this side, and I have 2, 3 carbons. So now I'm going to have to increase this carbon over here. So I've got 3 carbons. And let's see, is it balanced what I've done so far? So we have silicone 1, we have oxygen 2, we have oxygen 2 over here, and we have carbon 3, and we have 1, 2, 3 carbons. Yep, this checks out. So this is balanced. All right. So does everyone understand? If you need me to write these out clearly, because I know they're sort of jumbled in this one, just let me know. And it looks like those are all the problems. So thanks for tuning in, and we're going to start next on chapter 1.4. All right, thank you.